We got a few minutes, right? The lunch, before lunch. So I want to open up and open the floor for discussion. I'd like to, depending on how much time we have, I'd like to alternate between targeting the success and the challenge. So anyone want to share a success story and relate to what our panelists have been talking about? Something? Yes?
Well, the success story, I already have an electric car, and thank you for your efforts in that direction. I had a question, though, about the current opportunity for offshore generated power to directly connect into the grid. Is there an AC/DC issue with development of the power resource and the connectivity? And what are some of the methodologies that we might use to make this more of a, perhaps even a net export for a place like Maine?
Excellent question, thank you. As you know, the turbine is only a piece, and if you can't get the power to shore, you don't really have a project. So the whole planning effort really has to account not only for the generation aspect, but for the transmission and distribution aspects of the project. We did a study, and you can go to the web, looking at connectivity of offshore wind in the Gulf of Maine. Where can we plug in small demonstration projects to start with, and when can we plug in larger demonstration projects? And there's a lot of opportunities to do so. There's as you know, we have in Wiscasset, Maine, an existing nuclear power plant that was shut down a long time ago, and a large electrical infrastructure there at that facility. So one potential site to bring in a large either AC or DC or HVDC cable could be that site. In terms of smaller project, there's a whole bunch of places you can plug into the grid if you're looking at just demo projects in that 20 megawatt range. The other option, of course, is, and people are talking about that as we speak, as you know, there's plans for what we call the Green Line. The Green Line is a plan, and you go to the Chimbro website, and basically is to bring land-based wind resource connected to the large population centers south of Maine, which is in Massachusetts and so forth. That would be an undersea high-voltage DC cable that would allow us to connect those resources to the markets, if you wish. And I think you put your finger on it. We can use some of this energy, but we can't use it all the time. So somehow we got to get it to the marketplace as well. So those plans have to be developed in conjunction with the technology, the offshore wind development technology. Does that answer your question? Sure. I'm happy to give you those references on the web for those reports. Yeah.
Thank you. That was very interesting. Is there another question, thinking about the challenges some of the gentlemen raised?
A quick question for Nate. The floating generator that you showed, is that floating on the surface or below the surface?
That's below the surface. So we tested that in the prototype stage, and we do anticipate incorporating that into the next generation device. The other advantage of doing a moored system is the resource actually can vary by the depth. So you're able to place the turbine in the highest resource area, and also by having it underwater, you minimize impacts on existing navigation.
One for Habib. You said that you're creating a wind farm that's going to create 2 gigawatts of energy by 2040.
We have a demonstration project we're working on that we hope to have installed. That's 2 6-megawatt machines by 2018 off the coast of Monhegan Island, Maine. These are 2 6-megawatt machines, 12 megawatts, and that's a precursor, a stepping stone to potentially larger projects in the future. The larger project in the future will be farther offshore. We're looking at beyond the horizon, 20 miles plus beyond the horizon, so you don't see them from land. And those projects, of course, the size of those projects will be a function of the developers that will develop those projects. If you look at the needs in the New England area for renewable energy or energy coming up in the future, there's currently a tri-state RFP for renewable energy in Massachusetts, Rhode Island, so there's a need for renewable energy in those areas. The size of those farms that will be built, if you wish, to respond to this was a function of what the demand is and at that particular time. But our goal at the university is get to the point where we demonstrate the technology at full scale using these 2 6-megawatt machines by 2018. At that point in time, the private sector can take that on and develop farms from that point on. And the size of those farms is a function of the demand where they're built.
Have you calculated the savings or the cost of investment for the $6 billion savings?
Yeah, we've done a lot of economic modeling, not just ourselves as well, but we collaborate very heavily with the National Renewable Energy Lab in Boulder, Colorado. They've got analysts that look at these opportunities. Of course, the cost of electricity out of a two-turbine project is very high, the demo project. But if we build a 500 megawatt project in the early 2020s, they expect the cost of electricity for that using our technology to be 12.6 cents a kilowatt hour. Delivered to the grid. That includes the offshore cable. And then by the late 2020s, that price will come down to 7.7 cents a kilowatt hour, 7.7 cents a kilowatt hour. So it'll be very competitive at that time with existing electricity resources. Our goal is to develop a technology that in the 2020s would be competitive with other forms of electricity with no subsidies. And we think we have a technology that will get us there. So.
I have time for one last question. Sorry.
Sorry for dominating. I had a question for Habib. The government likes to deal with total life cycle costs. Are you doing anything in the area of research for decommissioning technologies?
Thanks for asking that question. Actually, that's one reason we went to concrete. It's because of life cycle costs. Typical offshore wind turbines in Europe today, or projects, have a lifetime of 20 to 25 years, after which they get decommissioned. That's the current lifetime. Land-based farms in the U.S. and in Canada as well have a 20 to 25-year typical lifespan. And a lot of that is due to the fact that the turbines themselves don't have a bigger life than that, and you can refurbish them, of course, but that's very costly. So typically 20 to 25 years is what most commercial developments on land and offshore in the world today are planning for. With the concrete technology we've developing, we wanted to do better than that. So the hull itself is designed for about 80 to 100-year life, and it's floating. So what does that mean? Every 20 years, we can tow the hull back to shore and repower the unit. That means just take the tower and turbine off top and then put a new turbine on and then tow it back to shore and remoor it to the seabed. Once you do that, then you don't have to worry about recommissioning, if you wish, or demolition, if you wish, of this whole infrastructure. And when you do that, actually the prices of electricity go down significantly. In the U.S., for example, if you look at the western state of Oregon or state of Washington, they have very low electricity prices for one reason. They built hydro facilities 80, 90, 100 years ago that have already paid for themselves. And all they have to do is replace the turbines on the hydro and maintain those turbines. And the price is at 4 cents a kilowatt hour down there. So we wanted to have, with offshore wind, we wanted to have the same idea. That's why we're building the hulls out of concrete, just like the concrete hydro dams, so that those will last 80 to 100 years. And every 20 years we repower them as well. So not only are we trying to solve the cost, the 20-year project cost, but we're also looking at 80 to 100-year life cycles for these. Yeah. Does that answer your question?
Yeah, question for Habib about the low cost of hydropower. What happens if we get energy contracts with Hydro-Quebec in the state of Maine? How would that affect the competition of your project?
Actually, it's a very, very good question. Let's talk about hydro. Actually, roughly 25% of the electricity in Maine comes from hydro dams. And there's been studies done that were capped out in Maine. We can't add any more hydro dams in Maine. We basically cannot add hydro in the state of Maine. If we're going to bring hydro in, it's going to come from the north. The beauty of hydro is that it's a great base resource, base energy, that can balance offshore wind. So if we're smart what we're doing here, we need to be working with our partners in the north and figure out how to balance large-scale offshore wind with the base load that hydro actually delivers. And that's happening in Europe today. In Norway, for example, they have a huge hydro resource. So the countries south of Norway are actually developing deals and cables with the Norwegians to balance offshore wind using the hydro resource that Norway has. So I think it's a great opportunity for collaboration right there. Thanks for asking the question.
Okay, I think with that question, I'll bring this session to a close. And I want to thank the three panelists for all the contributions they made. But I also especially want to thank Stephen and Stephanie for inviting me here. for this, for chairing this session and for this wonderful workshop they brought together. So, and thank you all for your participation.